Hi, this is David Quatello at Siemens. In today's Brain Shark, we'll be discussing the Siemens Quick Step Basics of Safety Switches course. So let's get started. Here are some of those legal trademarks that we have to mention. And here are the objectives of today's course. Upon completion of the course, you should be able to explain the need for circuit protection, identify fuse types and classes, explain the basic construction and operation of a Siemens safety switch, explain the operation and benefits of Siemens VB2 safety switches and visible blade designs, identify various types of Siemens safety switches, explain the difference between fusible and non-fusible safety switches, identify circuit protection ratings for various types of Siemens safety switches, and finally, identify safety switch accessories. This Quick Step course will have 3 parts plus a final exam. The first part is an introduction that covers basic overcurrent protection concepts. The second part covers enclosure and safety switch terminology. And the third part covers Siemens line of safety switches. And then we'll close it all up with a final exam. A safety switch is a common type of enclosed switch. Safety switches are generally used for 2 purposes. 1, as a disconnecting means for a service entrance, or 2, as a disconnecting means and fault protection for motors. The enclosure provides a degree of protection to personnel against incidental contact with live electrical equipment. It also provides protection to the enclosed equipment against specific environmental conditions. Safety switches may consist of a switch only, or may consist of a switch and fuses. There are 2 families of Siemens safety switches, general and heavy duty. As previously indicated, a safety switch can be used as a disconnecting means for a motor. National Electric Code Article 430.102 requires a disconnecting means within sight of a motor and the machinery driven by the motor. The NEC considers this to mean that the disconnecting device must be visible from the motor and machinery driven by the motor and not more than 15 meters, which is approximately 50 feet, away. NEC Article 430.102 does include exceptions. Refer to the full article for details. Regardless of where the safety switch is used, the function is to provide a means to disconnect and connect the load from its source of electrical power. With power removed, someone can safely service the machinery without coming into contact with live electrical components or having the motor accidentally start. Symbols are used in a diagram to represent components. The symbols commonly used for a disconnect switch are shown here. The switch is normally shown in its off or open state. Fuses are represented in an electrical circuit by either of the fuse symbols shown. A safety switch with no associated fuses is referred to as a non-fusible safety switch. A non-fusible safety switch has no circuit protection capability. It simply provides a convenient means to open and close a circuit. Opening the circuit disconnects the load from its source of electrical power, and closing the circuit connects the load. Circuit protection must be provided by external overcurrent devices such as a circuit breaker or fuses. In the top illustration, power is supplied to a motor through a non-fusible safety switch and a separate fuse. A safety switch can be combined with fuses in a single enclosure. This is referred to as a fusible safety switch. The switch provides a convenient means to manually open and close the circuit, and the fuse provides overcurrent protection. Current flow in a conductor always generates heat. The greater the current flow in a given size conductor, the hotter the conductor. Excess heat is damaging to electrical components and conductor insulation. For this reason, conductors have a rated continuous current carrying capacity, or ampacity. Overcurrent protection devices, such as fuses, are used to protect conductors from excessive current flow. Fuses are designed to keep the flow of current in a circuit at a safe level to prevent the circuit conductors from overheating. Excessive current is referred to as overcurrent. An overcurrent may result from an overload, short circuit, or ground fault. The first 2 types of overcurrent conditions are described in this course. An overload occurs when too many devices are operated on a single circuit, or when a piece of electrical equipment is made to work harder than it's designed to work. For example, a motor rated for 10 amperes may draw 20, 30, or more amps in an overload condition. In the accompanying illustration, a package has become jammed on a conveyor, causing the motor to work harder and draw more current. Because the motor is drawing more current, it heats up. Damage will occur to the motor in a short time if the problem is not corrected, or if the circuit is not shut down by the overcurrent protection device. Motors, of course, are not the only devices that require circuit protection for an overload condition. Every circuit requires some form of protection against overcurrent and the heat it produces. For example, high levels of heat to insulated wire can cause the insulation to break down and flake off, exposing the conductors. When exposed conductors touch, a short circuit occurs, and the circuit resistance drops to nearly zero. Because of this very low resistance, short circuit current can be thousands of times higher than normal operating current. Ohm's law shows the relationship of current, voltage, and resistance. For example, a 240 volt motor with 24 ohms of resistance would normally draw 10 amps of current. When a short circuit occurs, resistance drops dramatically. For example, if the above resistance dropped to 24 milliohms due to a short circuit, the current would increase to 10,000 amperes. The heat generated by short circuit current can rise to dangerous levels quickly, causing extensive damage to conductors and connected equipment. This heat generating current must be interrupted instantaneously after a short circuit occurs. Slight overcurrents can be allowed to continue for some period of time, but as the overcurrent magnitude increases, the protection device must act more quickly. When a short circuit occurs in an unprotected circuit, current will continue to flow until the circuit is damaged or the power is removed manually. The peak short circuit current of the first cycle is the greatest and is referred to as the peak let-through current. The electromagnetic force associated with this current can cause mechanical damage to electrical components. The maximum destructive energy let-through is a measure of the energy associated with this current. It is capable of producing enough heat to melt conductors. A properly applied overcurrent protection device will open the circuit quickly, limiting peak let-through current, IP, and energy. Article 240 of the NEC covers requirements for overcurrent protection and the use of overcurrent protection devices to prevent damage to conductors and equipment. You are encouraged to become familiar with this material. Various National Electric Code articles discuss overcurrent protection. Some of the relevant articles are listed below. Article 210 covers branch circuits. Article 215 covers feeders supplying branch circuit loads. Article 230 covers service conductors and their control and protection. Article 240 covers general requirements for overcurrent protection and overcurrent protection devices up to 600 volts. Article 430 covers motors, motor circuits, and controllers. It is beyond the scope of this course to cover this content, but it's useful to consider the intent of the information. In general, these articles are designed to ensure that conductors and overcurrent protection devices are properly sized for their loads, and that overcurrent protection devices provide the appropriate level of protection for conductors in the event of an overcurrent. Circuit protection would be unnecessary if overloads and short circuits could be eliminated. Unfortunately, they occur. To protect the circuit against these destructive currents, a protective device automatically disconnects the electrical equipment from the power source when a fault condition occurs. A fuse is the simplest device for interrupting a circuit experiencing an overload or a short circuit. A typical fuse, like the one shown here, consists of an element electrically connected to ferrules. These ferrules may also have attached end blades. The element provides a current path through the fuse. It is enclosed in a tube and surrounded by a filler material. As mentioned earlier, switches are normally shown in their off or open position. For the purposes of explanation, the accompanying illustration shows a closed switch symbol. This is not a legitimate symbol. It's used here for illustrative purposes only. In this example, a motor is connected to a voltage source through a fusible safety switch. The switch and fuse function as part of the conductor supplying power to the motor. When the switch is closed, current flows through the motor and the motor runs. Current flowing through the fuse element generates heat, which is absorbed and dissipated by the filler material. When an overcurrent occurs, temperature in the element rises. In the event of a transient overload condition, the excess heat is absorbed by the filler material. However, if a sustained overload occurs, the heat will eventually melt open an element segment. This will stop the flow of current. Fuses have an inverse time-current characteristic. The greater the overcurrent, the less time it takes for the fuse to open. This is referred to as the clearing time of the fuse. The accompanying illustration shows a symbol for an open fuse, commonly referred to as a blown fuse. This is not a legitimate symbol. It's used here for illustrative purposes only. In this example of a motor circuit, an overload has occurred, causing the fuse to open and remove power from the motor. As a result, the motor is stopped even though the switch is closed. Keep in mind that the fuse in the fusible safety switch is sized to protect the conductors that supply the current to the motor. Overload protection for the motor is normally provided separately, often by an overload relay. Short circuit current, which can be several thousand amperes, generates extreme heat. When a short circuit occurs, several element segments can melt simultaneously, which helps remove the load from the power source quickly. Short circuit current is typically cut off in less than half the cycle, before it can reach its full value. Non-time delay fuses, often called fast-acting fuses, provide excellent short circuit protection. However, short duration overloads, such as motor starting current, may cause nuisance openings of non-time delay fuses. For this reason, they are best used in circuits not subject to large current surges. Non-time delay fuses usually hold 500% of their rating for approximately 1/4 of a second, after which the current carrying element melts. This means that these fuses should not be used in motor circuits, which often have starting currents greater than 500% and lasting longer than 1/4 of a second. Time delay fuses provide both overload and short circuit protection. Time delay fuses usually allow 5 times the rated current for up to 10 seconds. This is normally sufficient time to allow a motor to start without nuisance opening of the fuse. However, a longer lasting overload will cause the fuse to open. Each fuse has a specific ampere rating, which is its continuous current carrying capacity. The ampere rating of the fuse chosen for a circuit usually should not exceed the current carrying capacity of the circuit. For example, if a circuit conductors are rated for 10 amperes, the largest fuse that should be selected is 10 amperes. However, there are circumstances where the ampere rating is permitted to be greater than the current carrying capacity of the circuit. For example, motor and welder circuit fuse ratings can exceed conductor ampacity to allow for inrush currents and duty cycles within limits established by the NEC. The voltage rating of a fuse must be at least equal to the circuit voltage. The voltage rating of a fuse can be higher than the circuit voltage, but never lower. A 600 volt fuse, for example, can be used in a 480 volt circuit, but a 250 volt fuse cannot be used in a 480 volt circuit. Fuses are also rated according to the level of fault current they can interrupt. This is referred to as the interrupting rating of the fuse and is expressed in amperes, often shortened to amps. A fuse for a specific application should be selected so that it can sustain the largest potential short circuit current that could occur in the application. This is important because if the fault current exceeded the interrupting ability of the fuse could rupture and extensive damage could occur. Fuses are grouped into current limiting and non-current limiting classes based on their operating and construction characteristics. Fuses that incorporate features or dimensions for the rejection of another fuse of the same ampere rating, but with a lower interrupting rating, are considered current limiting fuses. Underwriters Laboratories, or UL, establishes and standardizes basic performance and physical specifications in developing its safety test procedures. These specifications have resulted in distinct classes of low voltage fuses, 600 volts or less. The accompanying chart lists selected UL fuse classes. The accompanying illustration shows Class R type fuse holders, which feature rejection clips or pins that permit only Class R fuses to be installed. This prevents installation of a fuse with a lower interrupting rating, such as a Class H or K fuse. Okay, well that ends section 1, so let's jump into a knowledge check. Question 1. A safety switch with fuses in a single enclosure is referred to as a blank. Is it A, non-fusible safety switch, B, fusible safety switch, C, overload relay, or D, a motor starter? Question 2. The National Electric Code defines in sight as visible and not more than blank feet distance. Is it A, 50, B, 75, C, 100, or D, 125? Question 3. With an increase in current, heat will blank. A, stay the same, B, decrease, or C, increase? Question 4. A or an blank occurs when two bare conductors touch. Is it A, an overload, B, short circuit, C, an overvoltage, or D, undercurrent? Question 5. The level of fault current a fuse can safely interrupt is called its blank rating. Is it A, ampere, B, voltage, C, continuous current, or D, interrupting? Okay, now that you've gotten through the introduction, this part of the basics of safety switches covers enclosures and safety switch terminology. For the purpose of this course, an enclosure is the case that houses the components of an electrical device. The function of the enclosure is to prevent someone from accidentally touching an internal component that may have voltage applied and to protect internal components from damage. Various standards describe enclosure types. One of the more frequently cited standards is NEMA Standard 250. In addition to NEMA Standard 250, published by the National Electrical Manufacturers Association, UL 50 and UL 508, published by Underwriters Laboratory, Inc., are also important standards for electrical equipment enclosures. These standards provide enclosure descriptions, features, and test criteria for hazardous and non-hazardous locations. The brief descriptions provided in this course cover enclosure types available for Siemens safety switches. Within the industry, it is common to refer to the enclosure type numbers as NEMA types, but these type numbers also apply to UL 50 and UL 508. Type 1 enclosures are intended for indoor use, primarily to provide protection against limited amounts of falling dirt and contact with the enclosed equipment in locations where unusual service conditions do not exist. Type 3R enclosures are intended for outdoor use, primarily to provide a degree of protection against falling rain and sleet. They are not intended to provide protection against conditions such as dust, internal condensation, or internal icing. Type 4 enclosures are intended for indoor or outdoor use, primarily to provide a degree of protection against windblown dust, rain, splashing water, hose-directed water, and damage from external ice formations. They are not intended to provide protection against conditions such as internal condensation or internal icing. Type 4X enclosures are made of a material such as stainless steel and are intended primarily to provide a high degree of protection against corrosion, windblown dust and rain, splashing water, and hose-directed water. Another safety switch enclosure is a fiberglass reinforced polyester version of the 4X enclosure. This non-metallic 4X enclosure has no external metal parts. Type 12 enclosures provide a degree of protection against dust, falling dirt, and dripping water in indoor locations. but are not intended to protect against conditions such as internal condensation. Articles 500 through 504 of the NEC cover the use of electrical equipment in locations where fire or explosions due to gas, flammable liquids, combustible dust, or ignitable fibers may be possible. While you should never specify a hazardous location, it is important to understand the regulations that apply. It is the user's responsibility to contact local regulatory agencies to define the location as Division 1 or 2 and to comply with all applicable codes. Division 1 refers to a situation where hazardous materials are normally present in the atmosphere. Division 2 identifies conditions where the atmosphere may become hazardous as a result of abnormal conditions. For example, if a pipe carrying a hazardous material developed a leak, the surrounding atmosphere could become hazardous. Hazardous locations are further identified by class and group. Class 1, Groups A, B, C, and D apply to locations with hazardous gases or liquids. Class 2, Groups E, F, and G apply to locations with various types of flammable dust. And Class 3 applies to locations with ignitable fibers and lints, such as clothing fiber and textile mills, and flyings, such as sawdust. Class 3 is not divided into groups. Type 7 enclosures are intended for indoor use in locations classified as Class 1, Groups A, B, C, or D, as defined in the NEC. Type 9 enclosures are intended for indoor use in locations classified as Class 2, Groups E, F, or G, as defined in the NEC. Various hubs are available for attaching cable conduit to the enclosures. The term pole refers to the number of circuits that can pass through a switch at one time. This is the number of circuits that the device can connect and disconnect. The accompanying drawing, for example, shows a 3-pole safety switch. The 3 circuits are mechanically connected so that all 3 of the poles connect and disconnect that line and load simultaneously when the switch is operating. In this example, each pole is fused for overcurrent protection. Circuit configuration diagrams for 2- and 3-pole safety switches are shown in the accompanying illustration. As the illustration shows, safety switches may be fusible, non-fusible, or fusible with a solid neutral. Siemens safety switches are available in all the configurations shown in the accompanying illustration, as well as additional configurations. For example, Siemens heavy-duty fusible and non-fusible safety switches are also available with 4 or 6 poles. Throw is the term used to specify the number of circuits to which a conductor can be connected. All of the examples shown so far have been for single-throw switches. However, Siemens also offers double-throw switches in both general-duty non-fusible and heavy-duty fusible and non-fusible designs. Double-throw switches are intended to transfer loads from one power source to another or to connect a single power source to either of 2 loads. For example, the accompanying illustration shows 3-pole non-fusible safety switches. For either of the 2 applications, no power is applied to a load with the switch in the center, which is the off, position, and only one set of contacts can be closed at a time. In the application on the left, with the switch in the up position, the upper power source is connected to the load. With the switch in the down position, the lower power source is connected to the load. In the application on the right, with the switch in the up position, the power source is connected to the upper load, and with the switch in the down position, the power source is connected to the lower load. Okay, section 2 is complete. Let's go ahead and do a knowledge check. Question 1. NEMA type blank enclosures are intended for indoor use primarily to provide protection against contact with the enclosed equipment in locations where unusual service conditions do not exist. Is it A, 1, B, 3R, C, 4, or D, 4X? Question 2. NEMA type blank enclosures are intended for outdoor use primarily to provide a degree of protection against falling rain and sleet. Is it A, 1, B, 3R, C, 4, or D, 4X? Question 3. NEMA-type blank enclosures are made of a material such as stainless steel and are intended primarily to provide a high degree of protection against corrosion, wind-blown dust and rain, splashing water, and hose-directed water. Is it A, 1, B, 3R, C, 4X, or D, 12? Question 4. Hazardous location class blank is associated with ignitable fibers and lints such as clothing fiber and textile mills and flyings such as sawdust. Is it A, 1, B, 2, or C, 3? Question 5. Blank is the switch term used to specify the number of circuits to which a conductor can be connected. Is it A, pole, B, throw, C, break, or D, make? We are now in part 3 of the Quick Step Basics of Safety Switches course, and in this third section we will cover Siemens safety switches. The enclosure houses a switch mechanism, wire connectors, and an operating mechanism. A handle connected to the operating mechanism opens and closes the visible blade contacts. If the switch is fusible, the enclosure also houses the fuse clips. Provisions for locking the door and/or switch handle are provided. Switches use contacts to break the circuit and stop the flow of current. A typical switch assembly consists of a stationary contact, a hinged movable contact, and an operating handle. The hinged movable contact may also be referred to as a knife blade. Moving the handle to the on position closes the contacts and provides a complete path for current to flow from the power supply to the load. Moving the handle to the off position opens the contacts, interrupting the flow of electricity. As the contacts start to open, current continues to flow across the air gap between the two contacts in the form of an arc. Current continues to flow until the physical distance between the contacts is great enough to interrupt the flow of current. The point at which the arc is extinguished is called the break distance. Unlike the knife blade switch, the switching action of the Siemens 30 to 200 amp VB2 safety switch breaks the arc in two places. As a result, two smaller arcs are created and heat generation is reduced. The switching speed is also increased, since the breaking distance is effectively doubled. The overall result is enhanced performance and increased longevity. Also, in contrast to the knife blade switch, the VB2 safety switch blades are self-aligning, ensuring positive contact. Furthermore, another feature which enhances the speed of switching is the over-center toggle design. During operation of the switch, as the handle is moved past the midpoint, the switch suddenly and rapidly snaps from off to on or from on to off, depending upon the direction of movement of the handle. Besides enhancing the switching speed, this also gives a positive feel to the switch operation. The VB2 cover interlock prevents someone from opening the door while the switch is in the on position. Normally, the interlock also prevents someone from turning the switch on with the door open. However, for the purposes of testing or servicing, the door interlock is defeatable. As shown in the accompanying illustration, this can be done with a normal screwdriver. Every safety switch has a current rating, also called an ampere rating, which is the maximum continuous current the switch is designed to carry. Siemens VB2 general duty switches are available with ampere ratings from 30 to 600 amp. VB2 heavy duty switches are available with ampere ratings from 30 to 1200 amp. The maximum short circuit current that a safety switch can carry for a short time is called the short circuit current withstand rating. For example, Siemens VB2 general duty switches have a maximum short circuit current withstand rating of 100 kA, while the maximum short circuit withstand rating of heavy duty safety switches is 200 kA. The interrupting rating, which is the maximum current a fusible switch is capable of interrupting, depends on the fuse class used. Safety switches are also rated according to the maximum voltage they can handle. The voltage rating of the switch must be at least equal to the circuit voltage. In other words, it can be higher than the circuit voltage, but never lower. For example, a safety switch rated for 600 volts can be used on a 480 volt circuit, but a switch rated for 240 volts must not be used on a 480 volt circuit. The accompanying illustration shows the available voltage rating for Siemens safety switches. Siemens safety switches have 2 horsepower ratings for motor applications. This is referred to as dual horsepower rated. For example, a switch might have a standard rating of 10 horsepower and a maximum rating of 30 horsepower. The standard rating, 10 horsepower, applies when non-time delay fuses are used. The maximum rating of 30 horsepower applies when time delay fuses are used. The accompanying chart reflects the range of horsepower ratings for Siemens safety switches. VB2 general duty switches are intended for use primarily with supply circuits rated 240 volt AC, 250 volt DC, or less, where the available fault current is less than 100 kA. When used with Class R or T fuses, or less than 10 kA when used with Class H fuses. Switches are available with ampere ratings from 30 to 600 amp. The following configurations are available: 2-pole or 3-pole non-fusible, 2-pole, 2-fuse and solid neutral, 3-pole, 3-fuse and solid neutral, 4-pole, 4-fuse vacuum brake type. Fusible switches will accept the following UL class fuses: Class H, Class K, Class R. A Class R fuse clip rejector kit is available and required. Class T for 200 to 600 amp switches, and a 200 amp switches require a field adapter kit. General duty switches are available in a Type 1 enclosure, which is intended for indoor use primarily to provide protection against contact with the safety switch in locations where unusual service conditions do not exist. These switches have interlocks to prevent the cover from being opened when the switch is in the on position and to prevent the switch from being turned on with the door open. There is a front operable release for this feature. General duty 2-pole and 3-pole safety switches are also available in a Type 3R enclosure, which is intended for outdoor use and provides a degree of protection against falling rain and sleet. It is also able to withstand the formation of ice on the enclosure without damage, but is not intended to provide protection against conditions such as dust, internal condensation, or internal icing. General duty plug fuse type switches are available for 120 or 240 volt systems. 1-pole and 2-pole configurations are available. These switches have an ampere rating of 30 amps. Separately supplied 30 amp type S-plug fuse is required. Switches are available for use on 2-wire or 3-wire motor applications up to 3 horsepower. A non-fusible special application switch comes in a 2-pole configuration and is rated at 60 amps and can be used with motors up to 10 horsepower. There are also pull-out models available in fused and non-fused versions. VB2 heavy-duty safety switches are available with voltage ratings up to 600 volts, AC or DC, for applications where the available fault current is 200 kA or less. Ampere ratings from 30 to 1200 amps are available, the most commonly used configuration and enclosure options. The following configurations are available: 2-pole or 3-pole non-fusible, 2-pole 2-fuse, 3-pole 3-fuse, 2-pole 2-fuse and solid neutral, 3-pole 3-fuse and solid neutral. Fusible switches will accept the following UL class fuses: Class H, J, K, and R cartridge fuses for switches up to 600 amp, Class T cartridge fuses for switches up to 1200 amp, and Class L bolt-in fuses are standard for 800 and 1200 amp switches. Siemens offers a broad selection of heavy-duty safety switches with Type 1 or 3R enclosures. Selected heavy-duty safety switches are also available with other enclosure types, such as Types 4x stainless steel with viewing window, Type 4X non-metallic, and Type 12 with viewing window. Siemens safety switches with a window for viewing, visible blade position, and Type 4x stainless steel or Type 12 enclosures are available with 30 to 400 amp ratings. The window also allows viewing of indicating fuses for 30 to 200 amp fusible switches. Siemens heavy-duty safety switches are also available in 30 to 200 amp ratings with 316 grade stainless steel, Type 4x enclosures with or without a viewing window. These enclosures are more corrosion resistant than the standard 304 grade stainless steel enclosures. Type 316 stainless steel enclosures are especially suited for environments containing a high level of chlorine, or other chemicals commonly encountered in marine, waste management, food and beverage, petrochemical, and mining applications. Interlock receptacle safety switches provide a receptacle for powering heavy-duty, portable equipment such as refrigerated trucks, welders, and other portable electric tools. These switches are fitted with a Crouse-Hinds, Arcite, or similar receptacle which is interlocked to prevent insertion or removal of the plug when the switch is in the on position. The Crouse-Hinds receptacle switch requires a Crouse-Hinds 4-wire, 3-pole, Style 2 grounded APJ plug. Interlock receptacle safety switches are rated for 30, 60, and 100 amps. These switches are available with Type 12 or 4X enclosures. 4-pole and 6-pole heavy-duty fusible and non-fusible safety switches are available with current ratings of 30 to 200 amps. 4-pole switches are available with either a Type 1 or Type 12 3R enclosures. 6-pole switches are available with either a Type 12 3R or Type 4X stainless steel enclosure. These switches are commonly used as a disconnecting means for 2-speed, 2-winding motors. A 4-pole switch is also used in 3-phase 4-wire circuits when a switching neutral is required. Siemens enclosed photovoltaic disconnect switches have passed the extremely rigorous testing required by UL 1741 for photovoltaic disconnects with 3 separate 600 VDC circuits connected to a single 3-pole switch. Use of these disconnects reduces system cost in comparison to systems which provide separate disconnects for each circuit. A very hot arc is generated by the interruption of a 600 VDC circuit when under load. This damages conventional safety switch contacts and insulating material after a small number of operations unless the poles are connected in series to spread this destructive energy over at least 2 sets of contacts. In contrast, Siemens photovoltaic disconnect switches have powerful magnets in their line base which are strategically located and specifically aligned to disperse this energy and to very quickly extinguish the arc. The result is a line of disconnects that perform at a level far beyond that of any conventional safety switch. These switches are available with Type 1 or Type 3R enclosures in fusible and non-fusible versions with continuous current rating from 30 to 100 amp. Line and load lugs accept larger conductors than required by UL. This allows larger cables to be used to reduce voltage drop. A unique cover design features a rolled out front flange that prevents cuts and scrapes to conductors or the installer's hands. Additional features include a factory installed ground bar, door labeling as required by NEC Article 690, 2-point and 3-point mounting provisions are provided, and large top, bottom, and side gutters make wiring easier. Heavy-duty, double-throw, non-fusible switches are available with current ratings of 30 to 1200 amps. General-duty, double-throw, non-fusible switches are available with current ratings of 100 to 200 amps. Most products are available with a Type 1 or Type 12 3R enclosure. A few versions are available with a Type 12 3R or Type 4X enclosure. A full range of accessories is available for Siemens VB2 safety switches. Some of these are shown in the accompanying illustration. The accompanying illustration shows some of the other accessories available for general and heavy-duty safety switches. Heavy-duty switches are UL approved to accept field-installed copper lug kits. Equipment ground kits are available for all general-duty and heavy-duty switches. They come standard in Type 4 4X and Type 12 switches, and are field installable in Type 1 and Type 3R switches. Isolated ground kits are also available for 30 to 600 amp heavy-duty switches. Some circuits with a high degree of computer or other electronic loading require an isolated ground to prevent interference from the building ground and neutral lines. Auxiliary contacts are available only for heavy-duty switches. They come with 1 normally open and 1 normally closed, or 2 normally open and 2 normally closed contacts. A PLC auxiliary switch for 30 to 200 amp switches is also available. It has very low contact resistance, which is compatible with the low voltages and currents typically found in PLC circuits. Fuse puller kits are field installable in 30 to 100 amp heavy duty switches. Class R fuse clips are used to prevent the installation of non-current limiting Class H or Class K fuses. All general and 30 to 600 amp heavy-duty switches are field convertible to accept Class R fuse clip kits. Each type of safety switch has a catalog number. The catalog number provides a description of the safety switch. There are 8 parts to the catalog number for a Siemens VB2 safety switch. For example, as the accompanying illustration shows, a VB2 safety switch with the catalog number HF364NRCU has the following characteristics. It's a heavy-duty switch type, it's fused, has 3 poles, has a voltage rating of 600 volts, has an amp rating of 200 amps with a neutral, it's a Type 3R enclosure, and it has a special application of factory installed copper lugs. Okay, let's do a final knowledge check before the final exam. Question 1. Siemens VB2 general duty safety switches have ampere ratings from 30 to blank amps. Is it A, 200, B, 400, C, 600, or D, 1200? Question 2. VB2 heavy-duty safety switches have ampere ratings from 30 to blank amps. A, 200, B, 400, C, 600, or D, 1200? Question 3. Siemens VB2 heavy-duty safety switches have voltage ratings up to blank VAC/VDC. Is it A, 240, B, 480, C, 600, or D, 1200? Question 4. Siemens interlock receptacle safety switches provide a receptacle for powering heavy-duty portable equipment such as refrigerated trucks, welders, and other portable electric tools. Is it A, true, or B, false? Question 5. Blank switches are used to connect a single power source to either of 2 loads or to transfer loads from one power source to another. Is it A, single pole, B, double pole, C, single throw, or D, double throw? Alright, now it's time for the final exam, so let's get started. Question 1. A and blank occurs when 2 bare conductors touch. Is it A, overload, B, short circuit, C, overvoltage, or D, undercurrent? Number 2. Fuses are used with safety switches to provide blank protection. Is it A, undervoltage, B, surge, C, overcurrent, or D, phase loss? Question 3. Blank fuses are also called fast-acting fuses. Is it A, non-time delay, B, time delay, C, plug type, or D, class L? Question 4. A safety switch combined with fuses in a single enclosure is referred to as a blank safety switch. A, non-fusible, B, fusible, C, heavy duty, or D, general duty? Question 5. The National Electric Code defines in sight as visible and not more than blank feet distant. A, 10, B, 25, C, 50, or D, 100? Question 6. With an increase of current in a conductor, the conductor's temperature will blank. A, increase, B, decrease, C, decrease sharply, or D, remain the same? Question 7. Overcurrent protection is covered by NEC article. Is it A, 110, B, 240, C, 410, or D, 780? Question 8. A conductor's blank rating specifies the amount of continuous current the conductor can carry. Is it A, ampacity, B, impedance, C, inductance, or D, resistance? Question 9. Fuses have A/N blank time current characteristic. Is it A, direct, B, indirect, C, inverse, or D, proportional? Question 10. Class R fuses have an interrupting rating of blank amperes. A, 10,000, B, 50,000, C, 100,000, or D, 200,000? Question 11. NEMA-type blank enclosures are intended for indoor use primarily to provide protection against contact with the enclosed equipment in locations where unusual service conditions do not exist. Is it A, 1, B, 3R, C, 4, or D, 12? Question 12. NEMA-type blank enclosures are intended for outdoor use, primarily to provide a degree of protection against rain and sleet, but are not intended to protect against dust, internal condensation, or internal icing. Is it A, 1, B, 3R, C, 4, or D, 12? Question 13. The maximum ampere rating available for a Siemens general duty safety switch is blank amperes. Is it A, 200, B, 400, C, 600, or D, 1200? Question 14. The maximum ampere rating for a Siemens heavy-duty safety switch is blank amperes. A, 200, B, 400, C, 600, or D, 1200? Question 15. Siemens heavy-duty safety switches have a maximum short-circuit current withstand rating of blank amperes. Is it A, 10,000, B, 50,000, C, 100,000, or D, 200,000? Question 16. Siemens VB2 heavy-duty safety switches are available with voltage ratings up to blank VAC/BBC. Is it A, 120, B, 240, C, 480, or D, 600? Question 17. A Siemens safety switch catalog number beginning with GF3 indicates a blank safety switch. Is it A, general duty fusible 1-pole, B, general duty fusible 3-pole, C, general duty non-fusible 1-pole, or D, general duty non-fusible 3-pole? Question 18. Siemens blank safety switches provide a cord connection for heavy-duty portable equipment. Is it A, voltage pressure, B, double throw, C, interlock receptacle, or D, plug fuse? Question 19. Siemens VB2 30 to 200 amp safety switches use a blank switch action. Is it A, double break, B, knife blade, C, single break, or D, triple break? Question 20. The blank switches described in this course are intended to transfer a load from one power source to another or to connect either of two loads to a power source. Is it A, voltage pressure, B, double throw, C, interlock receptacle, or D, plug fuse? Well, that concludes the Siemens Quick Step Basics of Safety Switches. Thanks again for listening.